Okay. So we might just make a start, and I was going to talk a bit about how we use the design criteria, getting into the hydrotechnical design, particularly looking at the water balance, seepage, freeboard considerations, spillway design, and environmental considerations. And the first thing that we have to do is really get our water balance right. So the water balance for a tailings dam is pretty complicated. There's lots of things going on. So this diagram's intended to hopefully demonstrate some of the inputs and outputs. So we've got tailings come in and they've got quite a lot of water in it. Then there's rainfall onto the pond and also rainfall that's coming in from the catchment. Maybe there's diversions that are in the catchments to try and divert water from the dam, but we need to be pretty careful of how we treat those and whether they're reliable as far as some of the higher flows go. With the outflows, we've got the decant water return. We've got some sort of release to the environment. We might be treating the water through might be going through a treatment plant. There's evaporation and seepage, and it's very important when we're looking at seepage that we're considering the consolidation water, and that's quite often missed out. And then there's obviously water retained in the tailings. As the consolidation process is going on, there's still some water that's going to be trapped in the tailings. We need to understand how much that is. And then the final thing about the water balance will be the volume of water in the pond. And this is very sensitive to the water balance, so we need to get it right. So unlike water dams, the tailings dams have really got some other inputs that we might not consider in a water dam. And I've seen some pretty bad mistakes made in doing seepage analysis where you just do a conventional 2D analysis with the pond and you might consider rainfall, but quite often the consolidation water is not considered. And I'll talk a bit about that in a minute. And it's also pretty important to know what's going on in terms of drainage of the tailings and where the phreatic surface is, what that really means, what the pore pressures are below that phreatic surface, and how that all goes together. This is an example of a tailings dam just to demonstrate what is possibly happening inside a tailings dam. This is an upstream dam. And you can see up the top there's a cross section and there's 3 piezometers in a vertical installation. And the plots here are the pressures recorded in those 3 piezometers. The top one is the top piezometer, and the light blue line is the water level in the decant pond. And then the next line down is the middle piezometer, which is down lower in the tailings. And then the bottom one is the pressure in the foundations. So I do a bit of training of operators, and you give them this diagram and ask them to tell you what it really means, and that they do struggle a lot. But what it really means is there's vertical drainage going on there because we've got pressure drop between all those 3 piezometers, and it's indicating that the seepage is going out through the bottom of the dam. And it's also pretty important to know about the water inside the tailings itself. And on the left-hand side, we've got a typical hard metal slurry, solids SG 2.8. If we've got a 20% solids water or slurry in the process plant, that means for every tonne of solids, we've actually got 4 tonnes of water. If we go through a thickener, we might get to 50% solids. So we've managed to get 3 tonnes of that water off, but we've still got 1 tonne of water for every tonne of solids. If we discharge onto the beach, typically we might settle out to a density of around about, in this case, 1.1 to 1.2 tonnes per cubic metre. And that means that we've lost about half of our contained water in the slurry. So still a lot of water in there. And so what we do from there on determines a lot about how our tailings are going to perform and how much seepage we're going to get. And if we can get to a density, in this case of 1.9, that's what you might have deep down in the dam, with the consolidation process having gone on for a while, and we've got about, I suppose, what is it, 2/3 of the water might have been removed, but there's only two ways that that can be removed from the solids, and that's by evaporation or else by seepage. So if we haven't had evaporation, well, then all of that water is going to be trying to escape somewhere in the dam. And I've got this diagram, which when I first showed it to Andy, he got a bit confused about what this thing in the middle is. And that's really just a graph of density versus depth. So at the top of this is a cross section of the tailings dam with the pond and the beach and the natural surface levels. And this is meant to be demonstrating how the density of the tailings is loose at pretty low at the top, and then down deeper in the dam, it's going to be higher density because of consolidation. And to get to that high density, we need to have the water coming out. And so that's got to be allowed for in seepage analysis. And it can be quite a significant amount. And the example I've got there is that if you're raising the dam at 2 metres a year, which is what we typically find is our target in Australia, there's actually 1 cubic metre of water every year, every square metre of that dam. So that becomes a pretty significant water source, much greater than rainfall. And you'll find it's much greater than the seepage from a decant pond as well. And if we have a rapid rise rate, if you're putting the tailings in even more quickly than 2 metres a year, well, then we're going to end up a lot of water trapped. And the more water that's trapped, the more is going to contribute to seepage. This is a bit of a tricky chart, but it's got percent solids down the bottom and dry density up the side. And when we're putting the slurry in initially, we've got about 50% solids, and this is demonstrating how much water is coming out and at different times on the dam. At the settled beach, we've got 46% of the water comes out, and then by just leaving a beach drying, which is what we typically like to do, we can get quite a bit more water out, but we can never really get to the dilative condition in my experience, and we end up getting to some limit of the drying process, and then the efficiency of drying drops off dramatically, and we can't really get it to go any further in density. And then the last piece on the right hand side is kind of a back to front compaction curve showing optimum moisture content and maximum dry density that we might be used to in soil mechanics. And it is possible by mechanically working the tailings to actually get to that situation of removing more water and getting to a much higher density. In this case, you can see that the maximum dry density is over 2 tonnes per cubic metre, whereas most of our dams we're paying around about the 1.5, maybe 1.6 for that particular density of material, or SG material. I don't know if any of you have seen this machinery here. This is an amphi-roller, which is used in Australia in some mines, particularly alumina refineries, to get their red mud to a higher density, and that's a machine that's been designed to go out on sloppy tailings and farm it, what we call farming. And by doing it properly, you can drain more water out, and then you can get various other types of equipment onto the tailings. And from what I showed you there, it is theoretically possible to go right through the range of mechanical machines that you could get onto it, and eventually, theoretically, you could compact it to the same as earth works normally. So anyway, that's about the tailings themselves, but what we've got in our bulletin is a description of the water management on the dam, and we've defined a few criteria. This is a cross-section of the dam showing what we call the normal operating level, and then a maximum operating level, an environmental design flood storage, and then inflow design flood storage. And the point of all this water management on the dam is to, first of all, manage the dam safety, but secondly, looking at environmental safety. If the water quality is unsuitable for release, we've got some sort of controls on how much water we can release into the environment. And so the normal operating water level, we need to set that to the minimum we can, and it's usually got some sort of a requirement to get the water quality to a certain level before you pump it out of the dam. So there needs to be some sort of a minimum storage value to allow that quality to be achieved. And then there's the maximum water level, operating water level is based on typical normal seasonal flows that you might need to allow for without release of the water. And then we've got the environmental design flood, which is the temporary storage of any water that could cause environmental harm. And then above that, we would have either a spillway release or further storage of the inflow design flood. So the normal operating water level, typically controlled by pumping or could be by gravity decant systems. And it's very difficult to establish a level because we've got tailings coming in all the time. So the pond level is always rising because the tailings are taking up the water storage capacity. But we really should be trying to minimise this water level, first of all, to release or try and reduce the volume of anything that is released if the dam does breach. And also we should be trying to increase the size of our beach to try and evaporate as much water as we can and get the beach as dense as we can. The maximum operating water level needs to be established so that you maintain your environmental storage above that level, and there needs to be some sort of a trigger action response plan or some control to make sure that you don't exceed the maximum operating water level. So normally we'd have some sort of a TARP to give us some guidance on what we should be doing as the water level rises towards that maximum level. The environmental design flood is a bit controversial, but you know, quite normally our water levels, our water quality in the tailings dams are undesirable for normal release to the environment. So we need to capture that somehow. There's various ways to work it out, and we've given some guidance on how to do that. But it is an area that we probably need to do more work. It's been identified that we might do some more work on that in the future to give some better guidance on how you determine the environmental design flood. And in Australia, we do have a method that is similar to the consequence classification. So you can do a environmental consequence classification of the release of water, and then there's some guidance on what sort of storage capacity you should provide for different consequence classifications. But typically you get something like a 1 in 10 or 1 in 200 year flood storage. But I mean, personally, I really think this is something we have to minimise. And the more water we store on the dam, the more we're going to increase the risk of a failure through overtopping or piping, and there's other failure modes. And in some jurisdictions, like even in Australia, in one particular state, the regulations are that they determine the dam to be a no release dam. And so they're not allowed to even have a spillway, which to me, and we had a bit of argument about this in our committee, but personally, I think that every dam should have a spillway, and all the dams that I've been involved with, we have a spillway of some sort. Even if there's one case where there isn't a fixed spillway, but there is a plan to develop one if there is an emergency situation, but which personally I'm a bit dubious about, but at least that's better than having nothing. And obviously, if we are going to store water on the dam, we have to make sure that the dam is actually designed and is suitable for water storage. And our upstream dams really shouldn't be considered suitable for water storage. Okay, I want to get into talking about PMFs if I can help it, but we need to consider that when inflow design floods are occurring, it's going to be at a time when the ground is saturated. So typically we use runoff coefficient of 1 if we are trying to calculate floods. I don't know if Malcolm's going to put his hand up about that, but and also things like rain on snow events. I mean, I'm from a place we don't have that sort of problem, but some of our committee members are in cold climates, and I was reading a paper in the poster papers about this question. It's quite interesting, and I imagine it makes life very tricky when you do have freezing and snow and things like spillway blockage as well. That was pretty interesting. And spillway blockage by landslides, we've got some of the projects I'm involved with, we need to consider that. If we do have a spillway, we've just got to go through the normal hydrology of calculating the routing a flood through to determine the spillway capacity. So spillway versus flood storage. In our bulletin, we say that a spillway should be provided or at least planned for as part of the emergency response plan. So that's our recommendation. If we do want to store the IDF, I mean, I think most of us agree it's probably not that desirable, but in some places we have to. We need to think about this question that Malcolm raised about multiple storms. What is really, it's a pretty controversial question about how much storage you really should provide. And it's all very well to think about storing a PMF or something like that, but how long does it take you to get that water out? And what's the risk of some more water coming in while that's happening? So it's a pretty interesting way interesting problem to determine what sort of storage capacity you might provide on a dam if you don't have a spillway. And once again, if you do decide that you can live without a spillway, because it's quite difficult to put the spillway on in some cases when you've got a dam that's being progressively raised. And so it's easy to say, oh, don't worry, we'll just put an emergency spillway in if the flood level comes up near the crest. But, if we're talking about extreme weather events, it's potentially impossible or impractical to actually do any work on a dam. Some dams could survive an overtopping event. I'm interested yesterday to see the Norwegian method of riprap, which was they had riprap on both sides of the dam. Whether that was designed for overtopping, I'm not sure, but some dams could survive overtopping. I'll show you some good ones in a minute. But I guess the important thing to me is the added risk associated with storage of water that we'd really like to avoid. And so the ideal solution, and there are some cases that I've been involved with where you are able to have an off-dam storage. So these are some examples of spillways that I've been involved in tailings dams. The top middle is a roller compacted concrete. This one on the left is an overtopping spillway with coarse rock. Gabions here on the bottom left. On the right is a spillway on an upstream raised dam where the spillway section is designed as a downstream construction. So it can then have a spillway that's put on there that'll last for several years of lifts. And the top right is flow through. So we had several projects where you're able to dump coarse rock in a way that it segregates and creates drainage at the base of the dump, which could be a dam. And this is an example of a dam that didn't work. This is in China. And I went to China to do an inspection of this dam, but found out that it failed the year before. And in this case, they had pretty good spillway system. It wasn't a surface spillway. It was a tunnel, like a glory hole type of thing, with very large decant structures that were upstream and a tunnel that went through the foundations of the dam to the downstream. But unfortunately, they had something like a 1 in 200 year event, and there was a lot of erosion of that sort of. You can see the steep countryside around with fairly bushy kind of vegetation, so there was a lot of erosion. A lot of that vegetation got washed off, floated around in the dam and blocked off the screens that led to these spillways, and so the water level rose. And also, this is a good example of why you couldn't build an emergency spillway, because at the time of that event, the power went out, the telephones went out, the roads were washed away, so the site had absolutely no way to warn this village downstream, which you can just see in the bottom right corner. So about an hour after the water overtopped the dam, it failed and killed, I think, 4 or 5 people in the village down below. So it's a good example of not having a spillway, or not having a safe spillway, and also, you know, the things you really have to think about in an emergency response plan. Additional freeboard allowances really need to be carefully thought through. We recommended a minimum of 1, but there's a job that I'm involved looking at the moment, of doing a peer review actually in Papua New Guinea, and there's it's a pit backfill, or a big dam being built to close off an open cut pit, and we raised the potential for landslide in the pit's walls and what that would do to the tailings, and ended up they have to provide an extra 10 metres of freeboard to allow for the potential wave of the landslide cascading into the dam. So you need to think about whether you need any more freeboard and how that would be achieved. Water recovery can be by fixed or floating pump systems, or gravity. Mostly we're getting a lot more pumps these days, but you need to be careful that we're sizing these events for the same thing that Malcolm raised earlier. If we do get storm events, we have to plan to how to get them out. So, you know, removing the water after a flood could be the design parameter for the pump station or the decant, rather than the day-to-day operation. You need to be careful if you've got pipes through embankments that they have been the cause of some failures. What can go wrong? This left-hand picture is a pretty interesting one from a dam in the Philippines. That's a huge sinkhole that developed when the decant structure failed. So this is a structural failure mode, and you can see, or you probably can't see, but at the back here there's some concrete structures that are going down into the water. This is a 200-metre high dam, and in a pretty steep countryside, and the decant structure allowed the water to go down to tunnels down in the foundations that went through the abutments of the dam, and it was constructed by putting precast concrete panels progressively on the top of some concrete channel structures, and some of those panels failed down at the bottom and led to this outflowing of tailings. And it was quite a funny story. Well, a pretty good story the guys told me about it, that when this first happened, they thought, what can we do? So they decided they'd put a Hilux in the pond, and they pushed a Hilux into the pond, and it spiraled around for a few minutes and then got sucked down by the whirlpool, and nothing else, just nothing really felt on the dam. And the Hilux came out the tunnel all mashed up. So they decided to put the next size thing they had. It was a sort of a small truck, and that went in, and that had the same problem. So eventually they put a bus into the pond, and the bus spun around a few times and then got sucked in, and a few seconds later the mashed up bus came out. So eventually, after a few months, they built some 9-metre diameter concrete balls, and they rolled these. Well, they only needed one. They rolled it off the side of the embankment, and it went down right down to the bottom and got wedged into the breach, and it stopped the flow. So then they called for volunteers to go up the tunnel to inspect it. So conclusion: good water management's really important for dam safety, and the Mount Poly expert panel said best available technology needed to reduce the risk. If you're going to reduce the risk to zero, we really have to have zero water, and it's just not possible to do that. but we need to look at best available technology. How can we do our water management the best way? And at the time they were talking about converting everything to filtering, and that's a lot of pushback on that, and there are other ways to do it. So we've got to sort of think pretty carefully about what our water management is going to be. Try and avoid as much as we can water on TSFs, try and maximise removal, maybe consider off-dam environmental storage, and ideally if we could compact our dams, the better off we'll be. So thank you.